I've given you a very short tour, 1 week tour into groups. Now I'm cheating because the whole semester has been about symmetries in disguise, matrices, eigenvalues, commuting operators or matrices, then Fourier analysis. It was all really about symmetries. And now I want to bring a few aspects which I haven't had time to do, but in this series of snippets I covered, which is what happens when you start adding symmetries, making things more symmetric. The first thing that happens is you mix up pieces that used to be not mixed before. So as an example, I'll take a reflection. So far, we studied what happens when we move cyclically on a periodic chain. And we found out it's called Fourier representation of discrete chain, one-dimensional representations, which could be each characterized by some parameter q, which is integer 2 pi over number of things, q, times m, which is how many steps we went around. But very often, there's no reason to go anti-clockwise. The nature doesn't care. Our law is invariant the parity. So if I go to the left and right, I should be getting same results. So I can add reflection to rotation, the simplest thing that can happen. Now it used to be that this would now, if I go the other way around, it would just mean that I change the sense of rotation and minus I would show up in square roots of unity. And if I say I can distinguish left and right, then I have to put them together. They'll actually give me two-dimensional irreducible representations. So whenever you add a symmetry, you put more conditions on what you have, more restrictions. And that means that there are fewer options open to you after these things are imposed. And that'll mean that you'll have fewer representations. In particular, what happens here is because you're adding, I plus and I minus, you will end up with cosines and sines. And the representations will have this form, which we know from rotation group in continuum. They'll be two-dimensional. So that's one thing that symmetry does, and I'll give more examples of it. And now come, more sensitive political things. The moment you have additional symmetries, then the world stratifies into classes. For example, I'll use 3 disks as an example. One class of people are do-nothings. And that's called identity in mathematics. I look at something, I apply identity to it, meaning I do nothing. Or I can do something. Which is, what we call reflection. So for example, I can interchange 2 and 3, or I can bounce a billiard ball between 2 and 3. And the class of group operations that do something are called reflections in this case. There are 3 of them because I can exchange these two guys, or those 2 guys. Or I can be really a doer and I can do everything. So this is a class of people, who run around and get every place. So one way that I like to draw it is that, I can go from 1 to 2, from 2 to 3. In other words, I can take these 3 disks and rotate them by 1/3. And that's done by these 2 operations. And, I can rotate by 2/3, but morally they are in the same class. So that's the notion of class. So it says, when I have symmetries, I have to distinguish what kind of things, what kind of operations qualitatively exist. And even though, when I write them as matrices, they're all very different. Morally, we know that reflecting this way or that way is the same. So we know that it's in some sense the same. They're just reflections around the different axes, but what we call what axis is arbitrary. So adding symmetry always stratifies the world of all possible things into classes. So the first thing we have to do is understand that there are classes. Once we have that, then we remember what we have already learned in the Newton stuff, which is we can now produce different kind of functions by acting on them. So we take any function whatsoever over my space. And what I can do is I can say, well, I'll do nothing. Or I can reflect it in 3 different ways. Or I can rotate it in 2 distinct ways. And that is, I did a number of times, the most symmetric you can do. You take a function, do everything you know how to do it, add it all up, and average, divide by number of operation. And for historical reason, that's called A1, the most symmetric thing. Now, one thing I remember when I have a reflection, my image changes, which means that some sign changes. So the next natural thing is to look at reflections carrying minus sign, but rotation not carrying any sign. That's called the anti-symmetric representation, called A2. And then there are other things that happen. And now, I'm giving you some examples, and they turn out all to be written as group operator, a character of the operation for a given representation. And now these guys can be 2-dimensional, and not only, but there are 2 copies of them. So these are now things you have to learn about group theory. But basically, when you have classes, they need to be represented. They have representations. There is a totally democratic one. There is the one that separates, black from white. And then there is a complicated thing, which is, dances that they can do. And the amazing thing, I personally find it totally amazing, is this character. So what is a character? So it uses letter chi for character. Every group element has a character in every irreducible representation. For every class, I can take any group element in a class, I'll get the same character. And for every irreducible representation, like fully symmetric representation, we'll get it. And now this character is a complex number. I find it totally amazing that we are working with matrices of arbitrary sizes on large set, etc., and it suffices to take one of them which is simply a trace of a representation of the group element. If you remember, when you had a matrix, the trace was invariant, so that was good. But also determinant was invariant. The trace of group element square was invariant. No, it's just enough to take group element and produce its trace, and you get one number, and that defines everything in group theory. So that's what I find amazing. Now, we know this already. So for example, for cyclic group on an element, this is called Fourier representation. And character of mth element, so shift raised to power m, is a complex number, and very nice one. It was root of unity. So that's the simplest example. But this works always. So you always have a class. And then you always have a character. And, character splits, or the process of finding intrinsically orthogonal coordinate system in which action of every matrix that commutes with generates a group is just a number, just diagonal, how we started the whole course. That has some name, and that's called a mode. It could be a hyperspherical function, something in hydrogen, or it could be translation. So I find that totally amazing. So now what are these characters again? I mean, we can define them, but remember what we discovered about Fourier transformations, that when we looked at what they really do, we could write them as one matrix, unitary matrix, that took our states on the chain, on our physical chain, and changed the coordinates in the orthogonal system by just matrix multiplication. And on the left-hand side showed up what we call Fourier modes. So there is a unitary transformation. And, unitary is nice because it means that it's inverse, it's just its Hermitian conjugate. So you can go back and forth, costs you nothing. So that's what we learned. And now the amazing thing is that goes to theory of all finite groups, including the monster group, and all continuous groups, infinite groups, including all the rotations in 3-4 dimensions, all the way to magical exceptional group E8, which has 248 dimensions, and its subgroup is the monster group, the continuous group. And this this unitary transformation from our world to the orthogonal coordinate world, where action of every operator is trivial, it's just a number, it has a name. It's called character table. So you will find that in all chemistry and condensed matter physics books, and you might find that certainly in chemistry, it's totally crucial. And what is the character table? It's a matrix, which on the right-hand side, you multiply by a vector. Now, for Fourier components, these are just all components on every side of the chain, but now because we have the symmetries, they get stratified into characters. So do nothing is this guy. Then there are, our do something. There are two kinds of do something. You can flip along the long diagonal. There are two kinds of, do something guys, which are these sigma 1s and sigma 2s, two diagonals. And there are two kinds of rotations. You can rotate by 90 degrees and by 180 degrees, and they're different. So there are these guys and there are these guys, do nothing. So this is our world, but now it's been divided into classes. The matrix only acts on each class, and it produces irreducible representations. So what we used to call Fourier modes, now it's still orthogonal world in which all the subspaces are orthogonal to each other, all operators are block diagonal. But now what works on this world is, fully symmetric, fully antisymmetric, and then a bunch of other guys of different dimensions. And that's how every finite group is characterized. It's the generalization of what we learn about Fourier. But now it works for everything that can be described as a linear transformation. So it works for all subgroups of the permutation group, finite number of things. And then it works for all rotations in which parameters can be compactified, like run on a sphere or something. That's called compact groups. So to summarize, what I find amazing about all this is, from what we have learned so far, we have classes. So it's all about class. And to go from classes to space of separated irreducible subspaces, like different states of helium or whatever you need to figure out, you have to diagonalize, and that is a unitary transformation, just there's a matrix. And that matrix is all about character. First class, second class, da, 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 da. So once you compute a character table for any group, you know everything. You can compute any consequence of that particular symmetry in any situation, any realization whatsoever. So it goes from our world, where you be busy around and do different things, to space of orthogonal intrinsic coordinates, the eigenmodes of a matrix which has some symmetry. And that's called irreducible or IREPs, irreducible representations. So next week, I will show that this still works for continuous group and symmetries that you know. The big surprise next week will be that you know all about rotations in 3 dimensions, because that's where you live. But the nature has pulled nasty trick on you. Roger Penrose, in some sense, got Nobel Prize for it. Underlying structure of our 3-dimensional space is actually 2-dimensional complex spins and not 3-dimensional, sticks that we are used to. Totally amazing. So every week brings a profound surprise. The big surprise for me of this week are these characters. Who ordered them? But they solve everything.